Happy Thursday. Happy lesson 74. I'm excited about this one because we're going to return to an old friend. We're going to talk about some uniform motion problems. And we've talked about those before. Uniform motion implies distance, but remember it's got the little built-in caveat that the person who is walking or jogging or driving or whatever the heck they're doing is moving at a uniform rate of motion. They're moving at the exact same speed at the exact same time. It's a simplification we put into our distance problems to make them a little bit easier. But we have uniform motion, and this kind is something called with both distances given. All right, I'm going to explain what that means, but let's do a quick review of the different kinds of uniform motion problems that we have handled. And I'm pretty sure we handled all three of these last year in Algebra 1 if you were with me, but we've also covered them in Algebra 2 this year. The first type, and this is all outlined on page 309, so I'll jot that down. The first kind, remember we have the pictures, is where two people are taking trips that are exactly the same. And the distance of the first trip is exactly the same as the distance of the last trip. Another way to draw this picture would be, you know, when like they're taking the race together and one's running and one's crawling or whatever, right? But in both of these cases, D1, distance 1, is equal to distance 2. And since distance is equal to rate times time, we can say that rate and time of the first trip equals rate times time of the second trip. All right, so that's the first type of distance problem we have studied. The second kind looks either like this, where two trains leave the same station, one traveling north, one traveling south, and they travel a certain distance, and at the end they're X many miles apart. Or the other way we can do it is to say Susie left her cabin in the woods hiking toward the mountain, and Billy left his tent by the river and hiked toward the same mountain. At what time did they meet? Right? And so that version looks like that. And in these we would define, I forget which letter we used. I think it might have been N as the total. We would say that the rate and the time of the first trip plus the rate and the time of the second trip would equal that combined distance of N. So that was the second kind that we did. The third kind is where two people are taking a trip, and after 2 hours, they start at the same time, but after 2 hours, they're at a different place. And here we used N to describe this gap between their two trips. And in these, what we would say, or another way to do it might be that one person is running a race and the other person gets a big head start. And we find out how much the big head start is. So in this style, we used, you would figure out which was the smaller trip, and then you would add N to the smaller trip. So in our pictures, it would both be the rate times the time of the first trip plus that gap amount equals the rate times the time of the second trip. All right, 3 scenarios. And in all of these scenarios, there's a relationship between the two distances. Either we're adding them together, or we're saying they're exactly the same, or we're saying they're different, but we know exactly how much they're different by. Now, in this fourth kind that we're going to start right now, and I'm going to put that as letter D. If you look in the book, you won't see that, but it's a little bit different. In this one, what makes these stories unique is they're two different distances, and they probably don't relate to each other at all. And so let me give you an example, and it's very important that I tell you this. I'm going to example 74 rather, sorry. We just lost 50 lessons of our work. I'm going to do 74 too, and I'll explain to you why I'm skipping the first one, and we'll go back to that. But I want to show you the first one. Okay, there's a girl named Atalanta.
The second one, you said the first one, and it was confusing.
Oh, okay. We're doing the second one. We're doing 74.2. Atalanta ran 4 times as fast as her challenger. I'm simplifying the notes for this a little bit. In fact, she ran 80 miles in 2 hours less. She ran 80 miles in 2 hours less than it took her challenger to run 28 miles. You don't necessarily have to copy this. This is right in the book. But I want to write it down so that I can underline and circle key pieces of information as we go. How fast did each of them run? And how long did it take them to run? So again, I'm simplifying a little bit here. Okay, I don't know about you, but I look at this and I go, oh my gosh, this looks really hard. But here's the way we start to break it down. We know, I'm scooting this up. Is that okay, Jane? Mm-hmm. Okay. So here's what makes this a type D problem. Atalanta, she ran 80 miles. Her challenger ran 28 miles. But their trips don't have anything to do with each other. It's not like one of these where they were running the same course and there was a distance between them. And it's not like one of these where their trips add up. They're running 2 completely different, and it's not like one of these where they were running exactly the same. They're 2 completely different distances. So here's the way that we map this out. And what I'm going to do is I'm going to call this one DA for Atalanta. And I've never heard that name before except in this book. And every time I do this problem, I go, what kind of name is that? But in any case, she ran her trip. It's 80 miles. The challenger is going to get a littler bar because her trip is shorter. And this is, I'm going to call that DC because that's the distance of the challenger. That's the only way this person's identified in our problem. It's so sad. Her trip, I'm going to assume it's a girl running this one, she ran 28 miles. We don't have any other way to relate those distances to each other than just to consider them 2 completely different things. So that is why this is a type D problem. It's 2 different distances that don't have a relationship to each other. So what we're going to have to do is we're going to have 2 pictures, and therefore we're going to have 2 equations. So we can start really simple because this is super easy. We know that the rate of Atlanta times the time of Atlanta is going to equal 80 miles. And we know that the rate of, I'm going to call her Cupcake, times the time of Cupcake is going to equal 28 miles. So that is fairly straightforward and simple to get to. The question is, if we've got 4 variables, that means we need 4 equations in order to solve it. And right now, dang it, we've only got 2 equations. So we need to keep going. So let's take a look at our story again and see if we can pull more information out of it. Okay, Atalanta ran 4 times as fast as her challenger, Cupcake. So if we're looking at the rates, we know that the rate of Atlanta equals 4 times the rate of Cupcake. Sometimes it's tempting to want to say that the 4 goes over here by Atlanta, but if you think about it, she's running faster, right? She ran 4 times as fast. So let's say Cupcake's running 1 mile an hour. That means Atalanta's running 4 miles an hour. That makes sense. So we definitely want the 4 over here. Okay, cool. So now we've used this piece of information. We've used the 80 miles. We've used the 28. Now we're just left with 2 hours less. So Atalanta is running in less time. So let's make an equation out of that. The time of Atlanta equals the time of Cupcake minus 2. And we stop for a second to make sure that makes sense. According to this, Cupcake took more time. And if you take Cupcake's time, subtract 2 hours off it, you'll get Atlanta's time. And Atalanta. And so let's double check and make sure that's what our story is saying. She ran her 80 miles in 2 hours less. Okay, so it looks like we have handled those tricky little pluses and minuses and dividing factors correctly. And when you look at the solution on page, this is example, I'll write it again so you can see it on this page, 74.2, and it's on page 310. So now we have our 4 equations. Now, if light bulbs are going off in your head, and sirens are wailing, and fireworks are exploding of excitement, then I know why. Because you recognize we've already done work where we were substituting with 4 variables like this. We've already done this. We did it a couple weeks ago. Not even that, last week, right? Maybe 2 weeks ago now. So we know how to do it. We have to pick a base equation, and then we have to plug in and start working. Yay! So we know our base equation is either this one or this one. So I'm going to put stars by them. So we just take a quick look at our other 2 equations and figure out which ones would be easier to substitute. And we can see right away that if we chose this one, then we would have to isolate the rate of cupcake, and we'd have to divide by 4, and that would put a putrid fraction into our substitution. Heck no, I don't want to do that. I don't know how you feel about it, but I don't want to do it. So we want to use this equation with this format, and that means we want to use this as the base. Make sense? We just avoid the fraction. Again, if you chose this one and worked with the fraction, you can still get it right. It just is a little bit more of a pain in the neck. So now let the substituting begin. We're going to put this in here. And here's our TA, so we're going to put this in here and see how far we get. Remember, at this point, we don't even know what we're going to be solving for. We're just kind of smushing things together to see what happens. So I'm going to substitute R8 equals 4RC. So I substitute that first. Now I'm going to parenthesis because I know I've got a 2-part expression here. TA is equal to TC minus 2. That looks like a Z, but I always hash my Z, so you know it's not. And that equals 80, yeah? So now we distribute. I knew you were thinking that. I was going to call on you, Lydia, and I knew you would know to distribute. So now we multiply 4RCTC minus 8RC equals 80. And hallelujah, the heavens have parted and the angels are singing, because now we see exactly where to plug in our RCTC, our rate and time of cupcake, with this lovely number. I actually wanted to circle that part to show that that will go right there. So 4 times 28 minus 8RC, oh, I put my minus in a weird place, equals 80. So this is looking really good, you guys, because we will be able to simplify down to and solve for one variable. That's not an equal sign. That's confusing. All right? 4 times 8, or 4 times 28. I'm going to do that over here on the side. 32, 3, 112 minus 8RC equals 80. My brain tells me let's swim the 8RC this way to get it positive, and let's subtract the 80 this way to get those solid number fishies together. 32, that all goes away, that all goes away, equals 8 times the rate of cupcake. And one last step, divide by 8, divide by 8. And that tells us that the rate of cupcake equals 4. And I go back to my problem just to double check my units, and we're working in miles per hour, so I MPH it up. Make sense? The trickiest part that we've run into so far was setting up our diagrams and our 4 basic equations. But this solving, like I said, we've already done that, so it looks fairly familiar. Now that we've solved for the rate of cupcake, we can go back here to our 4 equations. I'm going to copy them on the next page so it's a little cleaner, and then we'll see how we can go from there. We're almost done. So, copying over you guys don't have to do this. I don't expect you to do this in your homework, but I just want you to be able to follow my train of thought. Okay, so those were our 4 original equations. Remember, those were the 2 we were deciding between for the base. We've decided that the rate of cupcake equals 4 mph. So let's just start plugging in. I'm going to choose this one. The rate of Atalanta equals 4 times the rate of cupcake, so that's 4. So I'm going to say that the rate of Atalanta is 16 miles per hour. Yes, we're getting them right so far. Now we have to figure out one of the time numbers. So we could use either one. I'm feeling fond of cupcake since we solved for her first. So I'm going to use this equation and substitute in my rate of cupcake there. So 4 times TC equals 28. Oops, I said 28, but I wrote 88. So I'm using this equation now and substituting in. I'll put that brackets around there. So this tells me that the time of cupcake, I'll divide both sides by 4. The time of cupcake is 7 hours. That's a lot of running. I wouldn't run for 7 hours, to be perfectly honest with you. That's a long time. And then we can use this equation, our time equation, to say the time of Atlanta equals 7 minus 2. So the time of Atlanta is 5. So there are all of our solutions. And again, if you were keeping up with your homework, you'll feel fairly comfortable with this process. All right, that is the strategy of these problems. I want to go quickly back to example 74 1 and tell you why I skipped it in the first place. And there's a perfectly good reason. This story is about Friar Tuck. No, not Fire Truck. Friar Tuck. I better write it down. Friar Tuck, he rode 24 miles to the fair in Nottingham at a leisurely pace. So here he is riding to the fair. He's going to be this dude. This is the distance of Friar. I'm having a hard time speaking. And his distance is 24 miles. Now, here's where it gets confusing. He stayed too long at the fair and he had to double his speed on the way back in order to get home in time. Wait a minute. He went to the fair and he's coming back. This could easily be shown in one picture, which means it's a simple problem like the first ones we learned way back. We have going to the fair and coming back. So why on earth would you have to do this as a type 4 problem with 2 different distances? And that's why I skipped it first, is because this problem does not seem to fit the description I gave you of this new kind of problem, because he is coming and going the same distance, and I'll repeat myself. It looks like it's this kind. And the answer is what I'm saying is true. You don't have to work this as this new style of problem. You could easily take this Friar Tuck problem and solve it using our old pattern of there and back problems, is what I usually think of those as, there and back. So Friar Tuck is kind of a bad example of this new type of problem because he doesn't have to, we're overcomplicating his situation to do it in this 2 different distances format. But that's what we're going to do. Just for the sake of argument, we're going to draw Friar Tuck out as 2 different distances. So the distance going is 24 and the distance back is also 24. That seems silly. Honestly, John, I think you could have done better. But go ahead, work together, solve that. The answers, the problem starts on page 309 and the answers are on page 310. Go ahead and work that problem as a 2 different distance program and see if you can write the 4 equations and then solve. Good luck.